Alright guys, here we're going to talk about the heating and the cooling curves. The heating curves is when the temperature is increased for a liquid, and the cooling curves when the temperature of the liquid is decreased. And it's not only limited to the liquids, it could be from the solids all the way to liquids and to the vapors and the reverse. When you're doing the heating curves, we're talking about adding in the heat, so it's going to be an endothermic process. And when you talking about cooling curves, you're going to be releasing heat, so it's going to be an exothermic reaction. So you may get a negative value for the energy when you're doing the cooling curves. What that really means, you're releasing energy. Other than that, it doesn't really mean anything. Let's look at this particular question, and it will explain what a heating curve is, and then I'll give you an example of a cooling curve, how you draw that. And I got these some values, some constants here that we're going to be using. For the most part, you guys are going to be given these values, and there are a few values that you may want to memorize. For example, the specific heat of water. The liquid water is about 1 calories grams over degree Celsius, or 4.184 joules over grams degree Celsius. So that's the only one you may have to really worry about. The other values for the specific heat capacity of ice, the vapors, the fusion, the delta H for the fusion, and the delta H of vaporization are going to be given to you. Here, the delta H are given in terms of joules over grams. All right, so keep in mind they could be given in terms of the calories over grams, or they might well be given in terms of joules per mole or calories per mole. So it just depends on what unit you're really looking into. Here we particularly talking about calories over grams or the joules over grams in terms of the energies. Okay, so the question says you have this 10 grams of ice, and it's starting at negative 10 degrees Celsius and it's going all the way to 120 degrees Celsius. Now, since you are increasing the temperature, it's obviously going to be an endothermic reaction. It requires heat for this process to take place. You do have to understand what happens at different phases. And this is something you want to memorize about the melting point and the boiling point of water. If it's any other liquid beside water, they will tell you what the melting points and the boiling points are for that particular liquid. But for the water, they expect you to know what the melting points and the boiling points are. So when I'm drawing the heating curves and even the cooling curves as well, you want to have this x-axis and y-axis. So on the x-axis, you're going to have the amount of heat added. So in this particular case, since it's a heating curve, you want to write down amount of heat or energy added on the x-axis, and on the y-axis you will have a temperature, and that temperature obviously in this particular case is going to be in degrees Celsius. Then you want to pick few points on the y-axis. Not You don't have to worry about picking up any points on the x-axis. And obviously, I'm starting at negative 10 degrees Celsius, so I do want to pick that point right there. So let's say this is negative 10 degrees Celsius. And the next point I want to pick whenever the phase change of that particular liquid takes place. Now, in this particular case, the phase change of water is going to take place at 0. So I'll write that down here, 0 degrees Celsius. That's when the fusion takes place or the ice is going to start melting. And then the next phase change that will take place is going to be at 100 degrees Celsius. So those points are something that you want to make sure you know. And obviously, if it's a water, you should know when the water freeze and boil. For any other liquids, they will tell you those points. And then your final point is going to be 120 degrees Celsius. So those are the 4 points you want to make sure you have on your y-axis. Now, when you're starting in the beginning at 10 degrees Celsius, so at 10 degrees Celsius, once you start adding up the heat, the temperature of the ice is going to go up. So the temperature of the ice goes up until it hits 0. All right, so that's how it's going to look like. So you have like a positive slope line here where the temperature is increasing and your amount of heat is also increasing. And that's the only way you can increase the temperature of the ice. Now, suppose I call this point A, and let's just call this point B. Now, by the time you get to point B, you are at 0 degrees Celsius, and this is where the temperature, this is where the ice is going to start melting. Now, the beauty of these heating curves and just this nature is you don't increase the temperature unless all your ice has been melted or the phase change has been taking place. So here you still need energy for that phase change to take place, but your temperature is not going to increase. So you will have a flat line here. So from B to C, you can say, okay, my phase change is being taken place where the temperature doesn't increase, but you still need energy to break those lattice bonds that are in between the ice molecules to make it a liquid. Okay, so then once everything is converted into the liquid at point C, now you're going to rise up the temperature again until you hit 100. So to rise up the temperature, you would be needing heat, so that's why you get another positive slope there. Then once it gets to 100, let's say point D, this is where the vaporization is going to take place, and your liquid is going to start converting into the gas phase or the steam in this particular case. And while that takes place, the temperature is not going to change. All right, so you will see another flat line here. Okay, and then once by the time you get to E, suppose you have everything converted into the steam, and once everything is converted into the steam, it's going to increase the temperature again until you hit 120. So, and that's our stopping point, obviously, and you could go very well to 150 or anywhere above that. Now, the question doesn't necessarily have to ask you from the solid all the way to the gases. It could be anywhere. It could literally tell you you're starting out with water that's at 50 degrees Celsius and you're going all the way to 120 degrees Celsius. So it's just a matter of being able to recognize what the starting point is and what the end point is and draw the heating curve accordingly. But this is the broad picture that includes every single heating curve you're going to be seeing in when you're going from the solid to the liquid and to the gas. Now, when I'm looking at these different points here, A, B, C, D, E, and let's call this F right there. Um, so let's say I'm going to be needing Q1 energy or Q1 heat to go from A to B, and then I'm going to be needing Q2 going from B to C, and I'm going to be needing Q3 going from C to D, and then I'll have Q4 going from D to E, and then Q5 when you're going from E to F. So there are actually two different types of energies being taken place here. So you have Q1 and then Q3 and then you get Q5. All right, and in these particular cases, you're changing the temperature. All right, so there is a temperature change, but the phase does not change. So whenever the temperature changes and your phase does not change, you will be using this Q equals MCAT formula. So Q is going to be equal to MC delta T formula to find what those Q's going to be for those particular fragments. Now, whenever there is a phase change, like for example, Q2 and Q4 involves the phase change. So during the phase change, the temperature does not change. So you really can't use Q equals MC delta T formula. Instead, you're going to be using Q equals mass times the delta H. For example, if you want to calculate Q2, then you would use delta H of fusion. And if you want to calculate Q4, then you want to use delta H of vaporization because you're changing from the liquids to the gases there. So, and then obviously your total heat for this whole process, so Q total is going to be equal to Q1 plus Q2 plus Q3 plus Q4 and Q5. So ideally you will have to calculate every single one of those and add those up to get the Q total. Now, if you were starting as in a liquid, then you may not have all five of those. It just really depends on what the starting point is and what the end point is. The other things I do want to mention here, when you are, so I'll change the color here. So when you are at going from A to B, all you really have is a solid. So sometimes they ask you those kind of questions, what you really have in those particular fragments. When you're going from B to C, you have the solid and liquid. So there is a conversion being taking place between the solid to liquid, but at a particular time you may have both of those in there until you reach point C. Now between C to D, all you're really going to have is a liquid, And then between D to E, you will have a liquid and the gas. All right, and between E to F, you only gonna have the gas in there. Okay, so let's worry about calculating those in now. So you suppose I'm trying to calculate Q1. So your Q1 is gonna be the mass of the ice, the specific heat capacity of the ice, and whatever the delta T or the change in temperature gonna be. So remember, the delta T is always gonna be the T final minus T initial. So the mass of the ice that's given in the question is 10 grams, okay? So I'll just go and write that down here, 10 grams, and then times the specific heat capacity of the ice. So those numbers will be given to you. Now I do have all these numbers written down in calories and in the joules as well. So it really depends which particular value you really want to use, or which unit you want to calculate the energy in. So if you want to use the energy in joules, then you use the one that's on the right side, like 2.06 and 4.184. And if you want to use in calories, then you use the one on the left. So let's say I'm doing it in the joules. So the specific heat capacity of the ice is going to be 2.06 joules over grams degrees Celsius. And then the change in temperature, it's going to be T final minus T initial. Now for that particular segment where you have Q1, which is going from A to B, at point B, your temperature is going to be 0. So your final temperature is going to be 0 at this particular point, and then minus your initial temperature was minus 10. So 0 minus minus 10, so that gives you a positive value there. So when you do this all math here, you got 10 times 2.06 times 10, and turns out it's going to be somewhere around 206 joules. Now, I do want to mention here these values that I have written, 2.06 in terms of joules. They may be slightly different depending on what book you're using, but they don't really run much difference. Like, you may see 2.1 instead of 2.06, or maybe you may just see 2.0 instead of 2.06. So they will be slightly off, but it doesn't really make a big difference at the end of the day. Okay, so that's your Q1 that now you got calculated. I'll go and circle that. Okay, so similarly, let's calculate the Q2 now. So Q2 is the phase change, and since it's a phase change, and I'm going from the solid to a liquid, I'm going to be using the delta H of fusion here. So the mass is still going to be 10 grams. Now the delta H of fusion, since we are dealing in joules, I want to stick with the joules here, so it's going to be 334 joules per gram. So 334 joules per gram here. And when you do this math here, your units cancels out, and it's going to come out to be 3340 Q2 joules. Okay, so far I got 2 of those in. Okay, let's calculate Q3 now. Okay, so Q3, if I go back and make sure, double check where the Q3 is, on that curve, the Q3 is going to be going from 0 to 100. So there is only a temperature change. The phase change does not take place there. So I'm going to be using MC for liquid water times the delta T. Okay, so the mass is still going to be 10 grams. The specific heat capacity of water is 4.184 joules over grams degrees Celsius. Now the change in temperature, which is going to be the T final minus T initial. So see, in this particular fragment on the Q3, your final point is D and your initial point is C. So C is at 0 degrees Celsius and your D is at 100 degrees Celsius. So it's going to be 100 minus 0, and that's going to give you just 100 degrees Celsius, 100 minus 0. Okay, so when you do this math here, what's that going to be? So 10 times 4.184 times 100, that's going to give you about 4184 joules of energy for Q3. Okay, so now let's calculate Q4. So if I go back and see what Q4 is, Q4 is only the phase change takes place. That's where the liquid goes on to convert to the steam here. And since it's a phase change, I'm going to be using the mass times the delta H of vaporization. So the mass is going to be 10 grams, and your delta H of vaporization is given here. So those numbers are going to be given, all those constants, and the delta H of vaporization for water is 2260 joules per gram. So it's going to be 2260 joules per gram. Okay, so when you calculate this out, it's going to be 22,600 joules of energy, and that's going to be your Q4. Okay, now similarly, we can go ahead and calculate Q5 here. So Q5, if I go back to the heating curve there, the Q5 is going to be going from E to F, and that's so when you're going from 100 to 120 degrees Celsius, and that means you're changing the temperature, the phase change doesn't take place, so you're going to be using the Q equals MC delta T. So those are the few important things you want to make sure you know before you start doing these questions. Calculate Q5. So the Q5 in this particular case, since it's going from 100 to 120, so there's a change in temperature. So since there is a change in temperature, we're still going to be use MC delta T. So in this case, it's going to be the C for the vaporization times the delta T. And obviously the mass is still going to be 10 grams. The specific heat capacity for the vapors that we have written down up there is going to be 2.03 joules over grams degrees Celsius, and obviously your change in temperature is going to be 120 minus 100 to about 20 degrees Celsius. And doing all this math, it's going to be 406 joules of energy here. So to get the total energy, I would have to add all those up. So Q total is going to be Q1 plus Q2, Q3, Q4, and Q5. And all we really got to do is just put those numbers in there. So we know Q1 is 206 joules. Your Q2 is 3340 joules. Q3 4384. The Q4 is 22,600 joules, and your Q5 is 406. So at the end of the day, the total energy that you're going to be needing will be the sum of all of them, and that comes out to be 30,737 joules. And I can go ahead and convert that into kilojoules since it's a bigger number, so I can go ahead and write down 30.7 if I want to just keep 3 sig figs kilojoules. So that's how much energy that's going to be required to make that transformation happen. So going from ice, so that's going from ice all the way, that's going from ice all the way to the vapors at 120 degrees Celsius. You could also have a cooling curve. So I'm not going to do a question, but I'll tell you how the cooling curve exactly going to look like. And suppose I'm doing the very similar question, but now I'm still using 10 grams of ice, but now my starting point is 120 degrees Celsius, and we're going down to minus 10 degrees Celsius. So now that's a cooling curve because you are going to be decreasing the temperature. So everything else will be the same. You have the x-axis and the y-axis. Now, in the x-axis, you will have the heat released. Because remember, you're not going to be adding the heat now, you're going to be releasing the heat. That's because it's an exothermic reaction. And you'll have a temperature on the y-axis. So your starting point is 120 degrees Celsius. Then you come down to 100 degrees Celsius. And you pick 100 degrees Celsius, that's because that's your phase change takes place. then you pick 0 degrees Celsius, and then your lowest point is going to be negative 10 degrees Celsius. You don't have to really worry about drawing this particular axis onto a scale. It could be a little bit off in terms of the scale. It's more like a qualitative. So if I'm starting at 120, when I decrease the temperature, the steam's temperature is going to decrease until you hit 100 degrees Celsius. So when you're decreasing the temperature, you're going to be releasing the heat, all right? And then once the steam hits 100 degrees Celsius, then you're going to have a flat line where the gas is going to condense onto the liquids. And once every liquid is once every gas particle is converted to the liquid form, so it's called that F, called that E, and called that D. So at point D, every gas particle is converted to the liquid form or has been condensed. Now you're going to start seeing a decrease in the temperature again and releasing the energy there up to point C there. And then once you reach point C, you're going to see another phase change taking place there. And that phase change will convert the liquid to the ice or the solid until you get to point B. And then at point B, once all the liquid has been converted to the ice, the temperature is going to drop down to 10 degrees Celsius there. And that's going to be our final point. So that's going to be our A. So this particular cooling curve is exactly opposite of what you see in the heating curve. And I can say to kind of keep this relevant to what we just done up there. And I'm going to say those Q1 to Q5 again. So that means this is going to be Q5 here. This is going to be Q4. This is going to be Q3. That's going to be Q2. And that's going to be Q1. Okay. Now, to calculate the Q1, Q3, Q5, you're still going to be using MC delta T formula because you're changing the temperature there. And to calculate the Q2 and the Q4, you're still going to be using Q equals M times the delta H formula. So that doesn't really change. That doesn't change regardless the type of the question. Now, what changes, however, all these values, the Q1, Q3, and Q5, they're going to be a negative value because you're going on to a lower temperature, and when you do a T final minus T initial, they will come out to be negative values. And then, as far as the delta H's go, like the delta H of fusion here is going to be a negative number, and the delta H of vaporization is going to be a negative number. And that's because, remember, when you're doing an exothermic reaction, the delta H is going to be negative. So here I have written down those as positive. So you just have to know when you're decreasing the temperature and when you're going from the liquid to the solid or from the gas to the liquid, you're going to be taking those delta H's as negative because those are going to be your exothermic processes. So when you do all this math, and I'll encourage you to do all this math here, the Q1, Q3, Q5, Q2, and Q4 by using the formulas that I have written down there, and then go ahead and calculating the Q total. So I'm just going to go ahead and write that number down. The Q total is going to be actually the same, the number that you got up the Q total earlier, which was like 30,950. However, it will be a negative number. So it's going to be negative 30,950 joules at the end of the day. So what that really means that you have released this much energy when you decreasing the temperature for that 10 grams of ice from 120 degrees Celsius all the way to negative 10 degrees Celsius. So that's the difference going to be between the heating curve and the cooling curve. And like I said, the most important thing is be able to recognize what formula you're going to be using and what points you want to have on your y-axis and be able to draw the heating curves. Make sure you know what particular segments have or what kind of phases you have. Sometimes they ask you questions on those. And other than that, it's just a bunch of calculations in these kind of problems. All right, so if you have any questions, feel free to leave any comments in the section below.